Okay, welcome back. So this time we're looking at the 1975 AB4 BC1 question. So I've got a function y equals x plus the sine of x on an interval from negative pi halves to 3 pi halves included. First thing I want to do is find all of the maximum and minimum points on the given interval and then justify the answers. So if I'm looking for all maximums and minimums, they didn't say relative maximum, they didn't say relative minimum, so I'm looking for the absolute maximum and the absolute minimums, which we've done a lot of lately. So how do I find absolute maximums and absolute minimums?
Okay, so I need to find the derivative. Then okay, equate that to 0. Then I need to find those critical points that I need
Okay, sounds good. So I'm going to copy this function here. We've got y is equal to x plus sine x on the interval from negative pi halves to 3 pi halves. And that's included. Okay, so what will happen if I derive this?
Okay, so the derivative of x is equal to 1, and the derivative of sine is cosine. No, no. Uh,
That's right.
okay, 1 sine x cosine x, yes.
Okay, so my derivative is 1 plus cosine x. I need to figure out when this value is going to have a relative minimum or a relative maximum, so I'm looking for all the critical points. How do I find critical points?
Okay, so I need to equate that by 0, and then I need to solve for x. So
Okay,
that will become
if I'm equating this to 0, that means I'm looking for all the points where the slope of my original function, since this is the first derivative, is equal to 0. If the slope is 0, that could be a relative maximum or minimum. So this is 0 is equal to 1 plus the cosine of x. How do I solve this?
okay, so that will become negative 1 is equal to the cosine, the inverse. Okay, all right. And so x is equal to the inverse of negative 1.
Okay, where is the cosine equal to negative 1 on the unit circle?
All right, cosine, which is negative 1, is pi.
At pi. Um, Now, unlike last time, we have bounds for our interval. We're not continuing forever. So that means there will be a set number of answers. We're not going to have an unlimited number of answers for x. So if you remember last time for the warm-up, um, when we were looking for our relative maximums and minimums, we ended up with infinitely many points. Every new rotation, I'm going to have another point that's coterminal with the other angles. But for this one, because I'm only going from negative pi halves to 3 pi halves, we don't even have, we have one complete rotation from negative pi halves to 3 pi halves, but we're not going to continue infinitely. So are there any other points between negative pi halves and positive 3 pi halves that would work? What other points would be coterminal with pi?
The coterminal of pi is 0 or 2 pi.
No, actually. So 0 and 2 pi are going to be the opposite side of your unit circle.
Uh, again, again, please.
Right, so let me do this graphically. So far you've got pi, which is right here. Let's do this. Okay, so we've got pi, which is right here. And then we've got bounds for interval. So I am bounded by this point at negative pi halves, which which means I went backwards by this much. So that's the start of my rotation, and then the end of my rotation is what happens if I go forwards by that much. Okay, so the question was, are there any points on this rotation where... I don't have a really good way of doing this, do I? Try again. Okay, we'll pretend this line keeps going on this side and comes out this way. Struggling with all the software today, but okay. So I've got so from negative pi halves, which is what happens if I go backwards by pi halves, I'm going to go forwards for my rotation all the way to positive 3 pi halves. Okay, when I do that, I want to know if I pass through any points that are coterminal with this point right here at pi. Okay, so I pass all the way around and I hit the point I want only once. So we have no points that are coterminal with pi. The points that would be coterminal with pi would be negative pi and 3 pi. Coterminal means we end at the same place, right? But negative pi is further back than where we started. And 3 pi is further forwards than when we end. So I start at here, which is negative pi halves. And then we go 0, positive pi halves, pi. That's the first point we wanted. 3 pi halves. So I never hit 3 pi, because to hit 3 pi I would have to keep going around again. And I never hit negative pi because when I started I didn't go back far enough in order to get here. I only went back to here. Okay, my points that are coterminal with pi are negative pi, pi, and 3 pi. It would keep going up by 2 pi every time. But on our interval, only pi works. Okay, I'm going to write the general form for this in a second. So I could say that all the values that work for this are pi plus 2 pi n. What did I do? Pi plus 2 pi n. There we go. But within our interval, only pi is going to work. Okay, so therefore x equals pi. So x equals pi is my only critical point. Is that the only point that I need to test for an absolute minimum or maximum though?
No.
What else do I need to test?
Okay, like you're asking to give you another point. What are the possible points aside from the pi?
So we just found the critical points, which is pi. But that's not the only point that could be the largest or smallest y value. What are the other points that could be the largest or smallest y value for our function?
Can you apply, let's say, if you're looking for 2 pi too?
We can't because that would get us outside of our interval.
So we will do the negative pi over 2.
Perfect. The start point and end point. The start point and end points are always possibilities as well. So we've got the point where a function changes direction, because if I have a high point or a low point, I would need to change direction if the relative minimum or maximum. But it's also possible for the start point and end point to be the highest or lowest value, right? So we need to test all of the critical points. That's the point where the function changes direction, and or points where the slope is equal to 0, and the start. I'll just say the bounds of the interval, and the bounds of the interval. Okay, so the points we need to test, the points I need to plug into my y value are negative pi halves, pi, and 3 pi halves. So I'm going to make a table really quick. Give myself space. So this is the x value and the y value at these points. If my x value is negative pi halves, coming back in. So we have found out our relative minimum and maximums at pi. We've got one critical point, but you also told me that we need to test the bounds of the interval. So I'm going to plug in negative pi halves, pi, and 3 pi halves into my y value. So if I plug in negative pi halves, what happens to my y value?
Okay, so that will become negative pi over 2 plus 1.
Okay.
So to simplify, that will become 2 plus pi over 2.
Close.
Negative 2. Negative 2.
So I've got negative pi over 2 plus 1, so that's negative pi over 2 plus 2 over 2.
Yeah.
So that is 2 minus pi over 2. Okay, if I plug in pi, what will happen?
Okay, if I have pi plus sine pi, so the sine pi is negative.
Okay, and the last one, 3 pi halves. If I plug in 3 pi halves into my original function, what will happen? So 3 pi halves plus the sine at 3 pi halves.
3 pi halves plus 1.
Okay, the sine at 3 pi halves?
Negative 1.
-1. Okay, so I need to get a common denominator again. If I get a common denominator for 1, what would I get?
So I have 3 pi minus 2 over 2.
Perfect. 3 pi minus 2 all over 2. Okay, so now I need to figure out which of these y values is the largest and which is the smallest. So I'm going to make an estimate really quick. So for this one, 3 pi minus 2 over 2, if I round down, then instead of being 3.14 whatever, I'm going to have 3 instead for pi. So 3 times 3 is 9, minus 2 is 7 on top, divided by 2 is 3.5. So this is roughly 3.5 if I round down. Pi is 3.1 if I don't round. So this is larger than pi. Okay, for this one, I've got 1 minus pi. Again, pi is roughly 3.1, so I've got 1 minus 3 over 2 is about 1.5-ish. So 1 minus 1.5 will give me a negative value. So if I was going to order these from least to greatest, this would be the top one is the least, the middle one's in the middle, and the bottom one's the greatest, because the top one's negative, the middle one's pi, and the bottom one, even when we round down, is greater than pi. Okay, so I have a minimum at x equals negative pi halves, the start point, and I have a maximum at x equals 3 pi halves, which was the end point of our interval. Any questions on what we did for that?
Uh,
I'm going to give myself just a little bit more room so I can throw that on one page. And we'll center these. Okay. So that leaves us with part B and C. Part B says find all points of inflection on the interval and then justify the answers. So how do I find a point of inflection?
okay, to find the point of inflection, I need to get the second derivative. So I need to get the derivative of y is equal to 1 minus cosine x.
Okay, so this is what you were saying. We can test all the points where the second derivative is equal to what?
Equate to 0, and then find the point of inflection.
Okay, it's second derivative is equal to 0 or what else? Is there any other way that we could change concavity?
To change the concavity, we need to test. You need to find the start point and the end point.
Okay, close. So we're looking at all points where the second derivative is equal to 0 and, I should say or. All points where the second derivative is equal to 0 or is undefined. If there were any points where the point of inflection was undefined, that would be a break point where something else could happen on the other side of that point for our concavity. Okay, so I'm going to copy our original function and our derivative that we had from last time, and then we can go from there to get the second derivative. So what happens if I derive this one more time?
Okay, so that will become the second derivative is equal to negative sine x.
Perfect. And if I set that equal to 0 and solve for x, what happens?
Okay, so I need to find the inverse of sine, which is equal to 0.
Okay, you said inverse sine of what?
0.
0. Okay, where is the sine equal to 0?
Sine is equal to 0 at 0, and pi, and 2 pi.
Okay, 0, pi, 2 pi, so I could say 0 plus pi n
Okay.
would be all possible values, but we don't have all possible values on our interval. We're only going from negative pi halves to 3 pi halves. So which of these values is on this interval?
So I can use 0, and I
0.
can use pi.
Perfect. So only 0 or pi will work for those points where the concavity is equal to 0. In order to test and see whether those are points of inflection, I need to see whether or not the concavity changes. So I'm going to plug values into our second derivative to see if the concavity changes sign about those values. So this is our x value, and this is our y pi prime at that x value. Okay, so I have two values to test at 0 and pi for my points of inflection. If I plug in 0, what's going to happen? Oh, I've done this wrong, haven't I? I need to test around these 2 points. Oops. Okay, I'm going to redo this a little bit. Instead of doing a table, we'll do a chart. Just made a chart of all the points where our concavity was equal to 0. That's not going to tell us anything we don't know. Alright, so what I should have done is something like this. So we said we know that the concavity is 0 at 2 points, at 0 and at pi. So what I want to do is I want to plug in points that are around these two values into our second derivative, which is here. To see what happens to the concavity. So I'm going to move this down just a little bit, and we'll go. So pick any point you think would be easy to test that is less than 0 that we could test into our pi function.
Can I use negative pi over 2?
I would rather not, only because that's the bound of our interval.
Okay.
So let's pick anything between 0 and negative pi over 2.
Okay, so I could say negative pi over 3.
Sure. What's the sign at negative pi thirds?
Okay, so that is a negative square root of 3 over 2.
Right, so I have negative of negative root 3 over 2 is a positive.
Okay.
Okay, any point between 0 and pi?
Alright, can I say pi over 2?
Yes.
Okay. So pi over 2, so it's negative.
Okay, and the last one, it needs to be a point between pi and 3 pi over 2.
Pi and 3 pi over 2. Can I say negative 5 pi over 2? No, negative 5 pi over 2. Oh, no, 5 pi over 3 rather. 5 pi over
5 pi over 3, 5 pi thirds is bigger than 3 pi halves, so that does not work. I need a point between pi and 3 pi halves.
3 pi half. Okay. 5 pi over 6?
No, 5 pi 6 is not quite to pi yet.
3 pi over 2? 3 pi over 2. Let me see.
On the unit circle, we've got two values that'll work. I guess 3 if you want to do the 45s. So we could use 7 pi 6. We could use 5 pi fourths. Or we could use 4 pi thirds. So 4 pi thirds? Okay, so 4 pi thirds. What's the sign at 4 pi thirds?
Okay, so that is 1 half.
No.
1 half, so negative. 4 pi thirds is 1.
I'll flash my chart again. Here's your unit circle. 4 pi thirds is down here.
Square root of 3 over 2.
Positive or negative?
Negative.
Okay, so I would get negative root 3 over 2 for the sign part. If I multiply by negative 1, that'll give me a positive. Okay, so I've got this going on for the bounds of my interval. Okay, so what are my points of inflection, just looking at this graph?
My point of inflection falls between 0 and pi.
0 and pi are both points of inflection. They're both points of inflection because we do change concavity at both of these points. Okay. So I'm going to copy our graph in here. We change concavity at both x equals 0 and at x equals pi. So these are our points of inflection. Okay. So this is my second derivative. I am going to have to graph this in my next one, sketch a graph of the function. So before I sketch this, I'm going to go back and kind of compile what we've done so far. I have 3 points that we know for sure. So I'm going to copy these in. We've tested all of these points already. I know that we have a critical point at x equals pi. So I'm going to go ahead and test that point as well. Do the same thing that we just did, but for a first derivative test. So for my first derivative test, I am testing about the point pi, which was our critical point. Into my equation for the slope, which I'm going to copy back from here, but the equation for the slope was 1 plus cosine x. And then again, we're bounded by negative pi halves and 3 pi halves. So if I plug in a value that's on our interval that is less than pi, what would be an easy number to plug in?
Less than pi. So I can say pi over 6.
Sure, if you want. So what's the cosine at pi 6?
Pi over 6 is 1/2.
No, cosine at pi 6.
Square root of 3 over 2.
Square root 3 over 2. So is 1 plus root 3 over 2 positive or negative?
It's positive.
Positive. And then I need a value between pi and 3 pi halves. So what's a value that would be between pi and 3 pi halves?
Okay. I have 3 pi over 2.
Say again?
Can I say pi over 6?
No, you cannot, because 5 pi over 6 is less than pi.
More than pi.
No, pi is 6 pi over 6.
Oh, sorry. So I can have 7 pi over 6.
7 pi over 6, that works. So what's the cosine at 7 pi over 6?
Negative 1/2. Negative.
No, cosine.
Cosine is the x value, right? 0 over 2.
Okay, so I'm looking for cosine at 7 pi 6. Right.
Cosine.
It is negative. Negative what?
Negative 1/2.
No, negative 1/2 is the sine. That's the y value. I want the x value.
Okay. So negative square root of 3 over 2.
Right. Okay, I'm going to show that graphically really quick because we had some trouble there.
Oh, maybe I always mess up.
I'm just going to redo this whole unit circle, but we'll do it in pi 6, I think. So here's our unit circle. If I split this circle up into 6 instead, so I'll have something like this. So this is, I want to split this up 6 ways. So let me do a whole line. Trying to split up this quadrant into roughly equal thirds. It's eyeballing, it's not perfect. So I've got something like this. Okay, so this is 1 pi 6, 2 pi 6, which is pi thirds, 3 pi 6, which is pi halves, 4 pi 6, or 2 pi thirds, 5 pi 6, 6 pi 6, which is pi, and 7 pi 6, which is where I wanted to get to. Okay, so at 7 pi 6, if I drop my lines, I've got something that looks like this. So my long side right now is my x value, and my short side is going to be my y value. Okay. Add detail since I can see you copy. There we go. Okay, so back to this. um, what's the cosine at 7 pi 6?
Okay. So negative square root of 3 over 2
Mm-hmm.
plus 1. So plus 1 2 over 2 plus square root of 3 over 2. So I have 2 square plus square root of 3 over 2. So that is positive. Why? One second. Square root of 3 over 2.
Okay,
Wait,
let's try to squeeze the square root of 3 for a minute. What's the square root of 4?
Okay, that is 2, so less than 2.
Okay, it's got to be less than 2. What's the square root of 1?
That's 1.
Okay, so it's got to be
So
more than 1. So it's more than 1, but less than 2. Okay, so I've got root 3 over 2. That's a value between 1 and 2 divided by 2. So I've got 1, 1 plus a value that is between 1/2 and 1.
divided by
Uh, okay, so if I do 1 minus 1/2, what would I get?
that is positive.
Okay, that would be positive. And then 1 minus 1 would be 0. So I'm between a positive number and 0. So this must be positive. Okay, I'm going to do that one more time. So we said the cosine of x was negative root 3 over 2. So this became 2 over, this became, I'll do this, 1 minus root 3 over 2.
Square root of 3
Root 3 over 2. This square root 3, we said is some number between 1 and 2.
Yeah.
So this is 1 minus some number between 1 and 2. 1 is less than x is less than 2. Over 2. So this whole fraction is between 1/2 and 1. That means this whole value, 1 minus that fraction, is going to be between 1/2 and 0. So it must be positive. Okay. Let me get rid of everything we don't need really quick. And we'll copy this graph over. Alright. So I've got all of our x and y values that we knew so far. I've got all of my information on the first derivative. And then we also did a second derivative test earlier. So I've got all my information on the second derivative as well. And with that, we're going to graph our function. So let me copy this. And we'll graph as best we can. Okay. Let's see if I can get all of this on one page. Canvas size. stretching a little bit. And our x and y values. Alright. So starting with the points that we know, I've got when x is negative pi halves, our y value is negative. So I'll be somewhere out here. When x is pi, my value is pi. And when x is 3 pi over 2, I'm going to be a little bit larger than that. Okay. From negative pi halves, the start of my interval, to pi, I gotta go to 0 because I've got a break here. Okay, so from negative pi halves to 0, I am increasing and concave up. Increasing, concave up. So if I am increasing and concave up, I'll have a function that looks like... maybe I should find the y value at 0 as well. Let's do that, so that'll only take a second. Before I draw this concavity graph. So my original y value was x plus the sine of x, so that's 0 plus the sine at 0, which is 0. So I've got another point I can plug in before I graph this concavity. We know that the point 0, 0 is on the function. Okay, so now I am increasing and concave up, we said, from the start of my interval to 0. Increasing and concave up. Something like that. And then after 0, I become concave down until pi, but I'm still increasing until pi. So I'm increasing and concave down until pi. Increasing and concave down until pi. Okay, at pi, my concavity changes from decreasing to increasing, but my function remains increasing. So I am increasing and concave up from pi to 3 pi halves. And we've got our function. Alright, any questions on what we did? Okay. Since I already have all the other information down here, I'm just going to copy the graph in and we'll be done. Okay, while we're here, I'm also going to jump over to Desmos. We'll graph this and just make sure our graphs match. Just let me throw this over to the left and we'll jump into Desmos. This was x plus the sine of x. So if I cut this from... this was negative pi over 2 to 3 pi halves. Then we've got a graph that looks like this. So increasing concave up until 0. Then I am increasing concave down until it looks like somewhere around here-ish, and I can't find the point. So we said this point was at... I already forgot. At pi. Okay, so this is pi and pi plus the sine at pi, which is 0. So at that point, I change from concave down to concave up for the rest of the graph, which is perfect. That's what we had. Alright, any questions on what we did?
Fine.
Awesome.